Hi everyone, I am Haram and I am with,
Mariam Aslam.
and we will be discussing compressing and sparsifying large language models. Our presentation is divided into two parts. I will talk about sparsification of large language models, and Mariam will discuss quantification of large language models. Here's the outline for today. I'll start off with an introduction. I'll talk about what sparsity is. Then we will extend the mixture of expert principle and talk about G shard. And after G shard, we will discuss our third paper, which is Col T5, a version of the long T5. We'll talk about its architecture, some evaluation and results, and then I'll hand it over to Mariam to talk about quantification. So, what is sparsity? Sparsity uses the idea of conditional computation. In dense models, all parameters are used for all inputs, and sparsity allows us to only run some parts of the whole system. And why we do that? We do that because it helps with efficiency, it helps with speed, it's good for energy consumption, and it's great for capacity generation. So let's talk about what a traditional transformer model looks like. So we have this input layer and we have the attention layer. Then we have these output tokens. These output tokens are then fed into the feed forward layer, and then we get some output which is fed onto the next layer. So the key innovation here in the transformers were the attention mechanism that allowed them to consider the entire context of the input data. And this was a substantial leap from the prior sequence models that process data one date element at a time. So there's a bottleneck here, and the bottleneck is here. So at scale, Transformer needs to tackle more data and complex problems, and with the huge number of parameters and operations needed, it makes them very resource intensive and leads to inefficiencies and limits their scalability. So, what's the solution for that? The solution is conditional computing or sparse models. So let's talk about it. So we're going to cross this traditional architecture off and we're going to make a few changes. So if you look closely in this diagram, we see that the changes we have made are over here. So we have changed this feed forward network into smaller sub networks and we're calling them MOEs. And then we have this gating mechanism that decides which input tokens go to which experts. And the rest of the model is same. We have the input layer, attention layer, output tokens. So yeah, what we did is we replaced this entire dense network with smaller set sub networks, and we are essentially making it a divide and conquer problem, which is going to be so good in terms of complexity and computational resources. So why are we doing that? We are doing that because it's, as talked about earlier, it's good for efficiency. So a traditional GPT uses all neurons and all matrices for forward passing. So this entire network we see here, all of these neurons are involved in every computation, which is extremely expensive. What if all the neurons are not needed and we only need these orange ones? We are essentially performing triple, quadruple the amount of compute that's essential. What if we split this network into smaller subnetwork and each performing a specialized task? In terms of language translation, if we take an example, this number one, this expert would deal with punctuation, for example, and number two would deal with article. So we are dividing this huge problem into a smaller problem, and it is very good in terms of complexity. So we saw that there was this routing mechanism that decided which input tokens go to which experts. So let's talk about it in detail. So the routing mechanism is essentially the network that decides which tokens go to which expert. It's actually a learned process. It's not static. It learns and adapts through training. So as the mixture of expert model is exposed to more data, The routing mechanism defines and refines its criteria for selecting the experts for different type of input tokens. So over time, this learning process leads to specialization of experts, and each expert becomes more adept at handling specific types of input tokens, which improves the overall efficiency and effectiveness of the model. So at inference time, the routing mechanism learned behavior allows the model to use only a fraction of the expert's compute, which is great. So we are essentially performing this amount of computation instead of using the entire network. So let's talk about the paper. The paper is called Efficient Large Scale Language Modeling with Mixture of Experts. So what they do here is they actually use this mixture of expert models at scale, and they see how this model performs at scale compared to dense models. So we see that this graph here in on the x-axis we have dense training zeta flops, and on the y-axis we have an MOE speedup factor. We'll talk about how this is calculated in the next slides, but right now you can just think of it as how much more efficient an MOE model is relative to a dense model, and a speed of factor of 9 would indicate that an MOE model can match the performance of a corresponding dense model using 9 times less compute. So let's talk about the results here. We see that they have tested their model in three domains. So they have tested in domain language modeling, which is testing their model on data that it was trained on. Then they have tested on out of domain, which is a red line, which is testing their model on data that it was not trained on. And then we have zero shot priming. So we see that the highest gain is for in domain language modeling. So MOEs are most efficient when evaluated in domain. And we see that there the gain is 18 and around 16 or 18 here. So dense models perform 18 to 16 times more better than corresponding MOE models perform better than dense models. So the lowest gain is for the zero shot priming, but it's still better. It's around 4 times better than a dense model. So let's talk about how the speed up factor is calculated. So here C of t is the computed cost function at a given performance level t. So they use interpolation here since they have only discrete values. In order to know the continuous values, they need to use interpolation. So they use the highest known value and the lowest known value, and then they use a ratio of how far the performance level T is between the lower and the higher reference performances. And then this is the computed cost function. And then the speed up factor is just a ratio of the computed cost of dense and the MOE. Let's talk about the experiments that they performed. So they trained autoregressive transformer models that roughly match the sizes and architecture of GPT-3. They use pre-normalization transformer blocks and GALU activations. And for their dense models, they use only dense attention, unlike GPT-3, which uses alternate sparse and dense, and they use top two expert model. And by top two, they mean that when the gating mechanism scores the input based on their relevance and expertise, they use the top two scoring inputs from there. So I want to talk about this table from the paper. So if we look closely, we have the training cost of GPT-3, dense GPT-3, and then they compare it with their dense model and their MOE model. So we see that the training cost of a 13 billion GPT-3 model is 32.67 zettaflops, that is. And that of an MOE model of 15 billion size is just zero point 0.3, which is a huge gap. And we see that these expert models are much better performing as compared to dense models. So they pre-trained their data, their model on a union of 6 English language data sets. I have listed them here and the links are attached too if you want to take a closer look, but I will not be going into too much depth about these. So let's talk about the results. So they evaluate their models based on two metrics. They check perplexity as well as performance. And the reason they choose to is because perplexity is not a great indicator of downstream performance, task performance. So they choose perplexity, which is the this confidence that a model has on its predictions. If it's higher perplexity, then that's not good. The model's not confident. And for the data specifics for in-domain data, they use the reserved portion of the training data set aside to test the model's performance. And for out of domain, they use the pile data set. Again, these are some of the results from the paper. On the left hand side, we have in-domain data. So this yellow line is for MOE model and this red line is for a dense model. We see that yellow line is constantly less perplexed. So MOE is better performing for in-domain. And even for the out-of-domain data, we see that the yellow line has lesser perplexity. This gap actually closes at scale. They don't talk about why, but the reason could be overfitting, but still it performs better than a dense model, constantly less perplexed. Yeah. So these are some of the other results. We see that uh, this is a speed up factor that we talked about earlier. So we see that the best result is for common crawl, and the reason for that is because it's closely related to their model's training data. And we did talk about how their model performs best in domain settings. And on the right hand side, again, we see that this yellow line has the best accuracy, which means MOEs are very good, especially when compared to GPT-3 and other dense models. So their accuracy is lesser than the accuracy of MOE. So why are we scaling? We are scaling because it brings dramatic quality gains, as we saw in the previous results. Especially for computer vision and language processing tasks, it yields consistent gains and has led to better classification. This brings me to our second paper, which is G-Shard. Um, it's not really an ML paper and more of an engineering paper because they talk about a framework. This is actually Google's framework called G-Shard, where they try to build a 1 trillion parameter model but don't quite manage to create it. So they go with the next best thing that they did manage to train and create, which was the 600 billion parameter model. So what they do here is they build a huge MOE model, 600 billion parameter, and they then uh, use parallelization to split their data into multiple machines. So it's the same concept as we discussed earlier, but it's coupled with partition. So here I've written that the large model scale does not come from increasing the depth of the transformer, which is the number of layers, but increasing the width of the transformer, which is the MOE model essentially. So they combine it with a hard routing to parallelize onto 248 TPUs, and they managed to train it in just 4 days. And it is based on something that's called SPMD, which means single program multiple data. And it's a concept used in parallel computing where a single program is executed by processors parallelly, but each processor works on a different set of data. So let's talk about the architecture of G-Shard. So this is the traditional architecture. We've seen that. And then this is the MOE architecture. We see that we have this feed forward layer, which we have split into multiple networks, subnetworks. And then we have the gating mechanism. So G-Shard uses alternate MOE layers with feed forward layers. So we have this MOE layer, then we have a feed forward layer, then we'll have another MOE layer, and then another feed forward, so on and so forth. And then here is what sharding really is. So they actually split this entire network onto different machines, and this entire thing is actually done by the G-Shard framework itself, and the user does not have to worry about the hardware details, which is the great thing about this paper. So every machine has one expert on it. So we have this one expert here, and then this number E expert on this machine, and there are E different machines essentially. So let's talk about the gating mechanism here. So this equation shows us the gating score of each expert. So here, this is the input. We feed it into the gate function and we get a score for each expert. And this is what is happening inside each expert. So we multiply the input projection with the weights, then we apply an activation function to it and multiply it with the output weights. And then the output of each expert is essentially the weighted sum of based on the gating score. So if an expert has a gating score of 0, we don't route any input to it, which intuitively makes sense. And they talk about the considerations that they had while creating this gating function. So they talk about load balancing. They create their gating function in a way that their input is uniformly distributed among each expert. So not a single expert is has burden, and every expert essentially gets the same number of input tokens. And then they also introduce an auxiliary loss, where the loss function penalizes if it constantly sends inputs to one expert. So it actually appreciates if the distribution is uniform. And then they have random routing. So random routing is where we send the input tokens to the top two experts, but then sometimes if the score difference between the two experts is a lot, one has a very high score and the other has very low, then they'll just neglect the low scoring expert in order to reserve the capacity of each expert. So how do we implement Gshard? As I discussed earlier, it's very efficient and easy to use. We do not users essentially do not have to do anything, and everything has been handled. User only adds annotations using the annotation API. So the Gshard framework comes with two main things. It comes with an annotation API that lets user decide whether or not they want something to be replicated or distributed. So the framework would essentially decide itself. 80% of the time, the framework would decide for itself whether certain inputs need to be replicated or distributed. But it lets the user have some control as well. So users can decide if they want something to be distributed or replicated. And then it comes with an XLA compiler, which is an accelerated linear algebra compiler, which decides which actually creates a compiled program based on the annotation API, and it just shards the input based on that. So these are some characteristics of the XLA compiler. It has unified compilation across frameworks, so it can work with TensorFlow as well as PyTorch. It handles the partitioning itself, so it breaks down large computations into smaller operations, and then it handles data communication as well. So when we are talking about partitioning, a lot of computation and communication needs to happen between partitions as well. And the user does not have to worry about that because the XLA compiler will do it itself. And we will talk about it here. So these are some things some partitioning considerations that the XLA compiler handles. The two main ones they talk about in the paper are padding and halo exchange. And For example, if a certain tensor is not does not have even dimensions, so it will not be uniformly distributed. So certain partitions would have more data than other partitions. So what XLA compiler does in such cases is it pads the tensor with either identity matrix or zero, and it then uniformly distributes that tensor. And in some conditions, for example, in convolution tasks, we know that we have a kernel and that sliding window needs to move over our input here. So in this animation, this sliding window is moving over the input. But what if when it reaches this edge here, half of its data is residing on the other partition? So what do we do in such cases? This area in this paper is called halo area. And what the compiler does is when it reaches a halo area, it asks for other partitions to send their halo areas, and they do this halo exchange so that each partition has the entire complete window so it can produce accurate results. And this again is handled by the XLA compiler, and we do not have to worry about it, which is the great thing about it. Let's talk about the experiments they did and the data sets they use. So the data set is mined from the web, and it's not available to us. It has documents for over 100 languages to and from English. So the model they train is for massive multilingual machine translation. So it's a machine translation model, and it's multilingual. So it translates from different languages to English. The volume is huge. It's a total of 25 billion training examples. And then they have imbalance in language pairs. So, say they have languages that have millions of training examples, but for some languages, they do not have a lot of examples for, and they call them low resource languages. And for baseline, they actually train bilingual neural machine translation models for each language pair, and then they compare the results with that. So these are some model variations. So they vary two variables. They vary the number of layers in their models, and then they vary the number of experts used. So in this table here, we see that they start with 2000 and they actually start with 128 experts, and then they move to 512, and then they move to 2048, which is their largest model. And then they start with 12 layers, 36 layers, and 60 layered is their largest model. So let's talk about some of the results. So we see that this blue line, so this is actually blue score, delta blue score. So this blue line here is the performance or the delta blue score, which is quality gain of MOE model with 36 layers. So we see that it performs the best. And the reason for that is because of the number of layers. So as the number of layers increase, the model, due to over parameterization, gets to learn a lot. And then this brown line is the 12 layer model, which also intuitively makes sense because we would not expect it to perform better than a deeper model, right? And then we see that as the scale increases, the quality gain increases as well, which is contributing to our hypothesis that models perform better at scale. So yeah, this is from the graph that we just talked about. We see consistent quality gains with deeper models. So we saw that the model with 36 layers performs better than the model with 12 layers. And then we see that we see improvements for high resource tasks with more experts. So as the number of experts increase, we see improvements. We see this graph going upward. So this is another graph that the model talks about. So let's first take a look at the red line here, which is the quality gain measured in delta blue score, which is a standard metric for evaluating the accuracy of machine translation tasks. We see that as we increase the model size, Yeah, we start off with 37 billion weights, and then we move towards 600 billion. And as we increase the size, the blue line, this right here, which is the training wall time, even as our model size increases, this blue line does not increase exponentially, which means that we our model is learning really well and is not computationally expensive as compared to dense models. So if you direct your attention to the dotted line here, it represents the computational cost in terms of TPU V3 core years. You'll notice that as we move from a model with 37.5 billion weights to the one with 600 billion weights, the computational cost increases only from 6 to 22 core years. This is just a sublinear increase when considering the 16-fold increase in model size. So it means that MOE models are able to achieve great translation quality in a fraction of time as compared to dense models. They actually talk about the time that their dense model took, and it was 235 TPU core years, and this is just 22. Let's talk about the training efficiency now. So, deeper models are more sample efficient and they converge faster with fewer examples, which is because of the acceleration effect of overparameterization, since deeper models have more parameters. We see that here. Uh, a model with 12 layer takes 995 billion tokens to reach a cross entropy loss of zero point 0.7, while that of 36 layers just takes 321 billion tokens, which is three times less than that. Let's discuss the performance now. So the largest model, which is of 600 billion size, can be trained in 4 days to achieve the best quality, while that of 96 layers and 2048 cores took 42 days, which is 10 times more time to train. They also talk about the memory consumption actually. So the memory consumption in G-Shard comes from three things. It's the replicated weights, which is the in the transformer feed forward layers, then they have distributed weights, and then they have activations, which is the output of each layer that is used in forward and backward pass. So if we look here, we see that as we increase the number of experts, so we started off with 128 experts and then we moved towards 2048 experts. And as we increase the expert size, our activation weights and our weights actually increase, which intuitively makes sense. But something really interesting happens at the end. So we see that here, instead of the activation weights increasing, we see a little decrease. The reason here is that as the memory size of the activation increases, it cannot be spaced in one partition. So the XLA compiler actually rematerializes this and just uses some of the activations in the memory, and then the others are computed during the back pass, which is another great feature of the XLA compiler. So, what are the key takeaways here? So, G-Shard uses SPMD framework for massive scaling. Then it provides us annotation APIs that let us decide which tensors we want on every machine and which tensors we want to be split on every machine. And then they are able to train a massive multilingual machine translation model of a 600 billion parameter size in just 4. Coming to the last paper, which is the conditional long T5. It is a version of the long T5 which uses conditional computation in a very different way. So the last two papers were talking about the same concept, which was the mixture of expert model. But here we have a different concept. They they actually use the sparsity in a very different context, which we'll discuss in the next slide. So we see that many natural processing tasks benefit from long inputs, but processing long inputs is very expensive. Why? because of quadratic attention complexity. So every input has to attend to every other input which is quadratic, and when the input is too long, it's unfeasible to keep it in to use it as it is. So as the input increases, not all tokens are actually important. So it's the theory of bag of words. So in a bag of words, only a few words are important, right? So this is the intuition behind conditional long T5. The paper is called Faster Long Range Transformers with Conditional Computation, and the intuition, as I discussed earlier, is that some tokens are more important than others, and we can achieve better quality for lower cost by devoting more computation to important tokens. And this is how they do it. So they have a light branch and they have a heavy branch. So they route all tokens through the light branch, and only the important ones go through the heavy branch. And the difference between these branches is that the light branch has light attention, which is local attention, and light MLP layer, and the heavy branch has full attention and a heavy MLP. So these are the three main components of Cold T5. They have routing modules that decide which input tokens go through the heavy branch. Then they have conditional feed forward in the heavy branch and a conditional attention layer in the heavy branch as well. Again, here the routing mechanism of Cold T5 is learnable. They just multiply inputs with a learned embedding to obtain routing scores, then normalize it, and then they select the top k highest scoring inputs, and they route those inputs through the heavy branch. And here again, this is what the conditional feed forward looks like. We have the light branch on every token, but only a certain amount of tokens would be fed onto the heavy branch based on their score. This is the score that we calculated in the last slide. And then for conditional attention, we know that the most tokens have simple interaction, but some tokens benefit from heavier processing. So conditional attention consists of light and heavy branches, and this is what it looks like. So we see that some rows just have blue boxes, but some have additional purple boxes as well. This is where we are adding heavy extra tokens for important input tokens. But for local attention, we are just taking the local span of windows. Let's talk about the training. So they pre-trained on a C4 dataset with a batch size of 256, and they fine-tuned using a constant learning rate of 0.001. And these are the models they used. So they used three variations: a base model, a large, and an extra large. For base model, it was 248 million, and for the extra large, it was 5.2 billion. These are the data sets. These are some of these are different, but most of them belong to the scrolls benchmark on which Cold T5 actually achieves state of the art. These are the results. So the average performance of the blue line is much better than the pink line. So the blue line is Cold T5, and we see that it performs much better. And if we take a look at the time, we see that it requires way less time as compared to the long T5 for inference as well as for fine tuning. So as I talked about earlier, it achieves SOTA on the scrolls benchmark. We see that the Col T5 extra large model speed is lesser and has greater F1 score than the long T5 and greater exact match accuracy as well. So they actually, the way they scale is not in the model size, but actually the input size, and we see that it scales to extremely long inputs and achieves stronger performance. So we see that the blue line has greater F1 score, and they start off with an 8K input length and they move towards 64K, and during all this time they take way less time as compared to long T5 and has have greater performance. They do some ablation studies as well, and we see that as we they actually, one interesting thing they do is they make the routing static. And as we make the routing static, we see that the performance degrades. The score, if you see the score, it's actually way less than the baseline. That actually contributes to the factor that it benefits from dynamically routing token as it learns to identify and give more importance to important token. And this indicates that the model is not just performing better due to having more parameters. They also discuss some limitations of CoL-T5 in the paper. They say that CoL-T5 applies conditional computation only in the encoder, and it does not apply conditional computation to the decoder because it's complicated, and they leave that for future work. And they also talk about its specialization over long sequences, so it has to be trained from scratch for other types of sequences. This is a small comparison I did between the three models. So mixture of expert uses a 1.1 trillion model parameter model, and G-Shard uses 600 billion, while CoL-T5 uses 5.3 billion. For sparsification, mixture of expert just splits the feed forward layer, while G-Shard splits the feed forward layer as well as does partitioning, while CoL-T5 splits by branching. Sparsification for mixture of expert is in the feed forward layer. For G-Shard, it's in the feed forward layer as well, but for CoL-T5, it's in all three layers. Mixture of experts uses top two experts. G-Shard uses top two and random routing, and CoL-T5 does not use any. For attention, mixture of expert uses dense attention. G-Shard also uses dense attention, but CoL-T5 uses a mixture of both. And for specialization, mixture of expert specializes in large scale data. G-Shard specializes in parallelization, and CoL-T5 specializes in long inputs. Now I will hand it over to Mariam to talk about sparsification.
Hi. So I will be discussing the quantization of LLMs. Let me just fix slides a bit. I think a couple of the slides are missing. Let me see the coming slides. Now, to overview their mixed precision quantization. So, every feature is quantized based on its magnitude. So, let's say we have this input tensor, and we have the weight matrix. Now, the input tensor will be divided into vectors, and the high magnitude vectors will be identified, and they will be multiplied normally in floating point 16, while the low magnitude ones, they will be multiplied in int 8. So they are multiplied with quantization constants, which convert the floating point 16 into int 8, and then and then the matrix multiplication is performed, and then they are dequantized to get the output in the final FP16. So basically, but this bottleneck matrix multiplication part is carried out in int 8. So this is the mathematical form of this, where the floating points, the total output is actually the sum of the floating point matrix multiplication operations and the int 8 matrix multiplication operations. This SF16 is the scaling factor, which is used to adjust int 8 matrix multiplication back into floating point 16. This is basically the dequantization happening. Now, discussing the vector-wise quantization, this is a form of block-wise quantization, but such that each row of the tensor or column of the tensor is used as a single vector, and it is independently quantized. Now, this improves the quantization precision for most of the features. Now, for example, if this is the input matrix and this is the weight matrix, A1, A2, A3, and B1, B4, and B7, this is the matrix, this is the single operation of multiplication that will form our output matrix. So these vectors are independently quantized. They have their own scaling constants, and then the output is calculated once all of the vectors are placed together in a matrix and summed and then dequantized. This is the mathematical form where the output is actually the multiplication of the dequantization scaling factor and the indate output. Indate output is calculated by independently quantizing a vector A and vector B. Basically, the input vectors, let's say the input tensor is made up of these two vectors A and B. So A and B will be independently quantized and they will be multiplied with the scaling factor to get our final output. Q over here is the quantization function. Now, going into more detail of the scaling constants, basically, what are the quantization procedures that they're using? So they have displayed their experiments using max quantization as well as 0 point quantization. Max is symmetric. It scales the input values by a constant derived from the largest absolute value in the tensor. So basically, it's 127 because int 8, that's basically just 2 to the power 8 minus 1. So it's the total number, it's the maximum number that can be represented in the int 8 representation, and it's divided by the maximum of that vector. So this ensures that the extreme values are captured, but it also leads to less efficient use of the available bit range. The more efficient 0 point quantization is the more efficient quantization technique is the 0 point quantization. It is asymmetric. It involves shifting of the distribution of the input values. So in this way, the entire range of the representation is used effectively, and this accommodates asymmetric data as well. So in this procedure, we will divide twice the uh, maximum number of maximum bit representation divided, and we will divide it by the max minus min. And then in the end, we will also add the vector multiplied by its minimum. So this accommodates the entire range of the bit representation, and this also reduces quantization error across the board. Now, these are some results from their paper. They've calculated their C4 perplexity, and as we can see in this table, excuse me. As we can see in this paper, max and 0 point max row wise, and vector point vector 0 point vector wise, they reduce, they worsen as we scale, and they actually after 2.7 billion parameters they perform worse. So after 2.7 billion parameters, the methods actually perform worse than smaller models. 0 point vector-wise quantization performs worse after 6.7 billion parameters. So you may notice that 0 point quantization has an advantage over max quantization, but it's no longer advantageous when used with the mixed precision decomposition. So as you can see, their method LLM Indate outperforms all existing methods, and it's really it's preserving the perplexity as we scale, and it's exactly comparable. It's very comparable with the 32-bit float transformer models. So they, even though this was not a part of their main focus, but they've also given some results related to the time complexity. So uh, they've noticed that the quantization overhead can slow inference for models with less than 6.7 billion parameters, as compared to the floating point 16 baseline. However, after 6.7 billion parameters, Uh, After 6.7 billion parameters, LLM int 8 runs about twice as fast for large matrix multiplications, in equivalent to those in 175 billion models. Uh, LLM int 8 is twice as fast, and there's also to note, like, even though LLM int 8 is not has some more overhead for models smaller than 6.7 billion parameters, these small models usually fit on most GPUs, and quantization is not really needed in practice. Now, moving on, we see that we are able to quantize the parameters in the feed forward and attention projection layers, but during inference. But what about training, and what about the attention function computations? So this moves us to our next paper, which is 8-bit optimizers using blockwise quantization. Now, these perform optimization in neural networks by using 8-bit statistics to maintain the performance level of 32-bit optimizer states during training. So this paper focuses on optimization during training, and they are also not focused on the weights. Instead, they are going to focus on the optimizer states, because optimizer states use about 33 to 75% of the total memory footprint during training. So what are these optimizer gradient statistics? So basically, regular optimizers in machine learning update model parameters uh, purely based on the gradient calculated from the current batch of data. But stateful optimizers like SGD and Adam, they keep track of the past gradients and use this information to inform updates. For example, SGD uses momentum for smoothing the updates, and Adam keeps track of the squared sum of past gradients to adapt the learning rate for each parameter. So this paper focuses on optimizing the memory footprint of these optimizer states. Now they employ blockwise quantization, and this approach reduces the memory usage of the optimizer states, allowing larger models to be trained within the same memory constraints without losing the performance benefits that come from using stateful optimizers. The key innovations in this paper are blockwise dynamic quantization and the stable embedding layer. Now, this blockwise quantization isolates outliers and distributes the error more equally over all bits. Uh, Basically, over here, they break down the tensor into smaller blocks or chunks, and they normalize each block independently for efficient computation and for processing in parallel. And this is the mathematical form of it. And they use the normalization constant for block B, which is the maximum absolute value within that block. So the quantized value of the vector is divided by the normalization constant, and this fraction is subtracted from the function mapping the jth element to its quantized form. Uh, they are basically using Ab's max quantization, which we will see later on. Now, why is this method good? Because it's robust to outliers. This is independent from intercore synchronization, because since we are dividing the blocks, and those multiplications, those computations are happening in parallel, so we don't need to do the intercore synchronization. So this enhances the computational efficiency, and this method also guarantees that the largest values are quantized without error. So this maintains the precision in the quantization process. Now they've also introduced this dynamic quantization procedure. So over here, this is basically a type of quantization where they adjust for both small and large magnitude values with high precision, and they are actually enhancing the dynamic tree quantization for tensors that don't need a sign bit by repurposing it for better precision in representing positive values. What this means is, this is about adjusting the quantization technique used in optimizers like Adam, which generally involves keeping track of the second state or a running average of the gradients. Since these values are always positive, the sign bit typically used to indicate negative numbers in binary representation is not needed. So the authors utilize this redundant sign bit to increase the precision of the quantization, thus allowing the optimizer to handle a broader range of values that the second state might encounter during training. So this modification helps to maintain the fidelity of the optimizer state representation. So this is especially important for large language models, which can have significant variations in the scale of gradient information. So this allows accounts for a wide range of magnitudes uh, in this Adam optimizer. So their other key innovation is the stable embedding layer. So basically, traditional embedding layers can become unstable with lower precision formats like 8-bit integers because the reduced precision can lead to large errors or instabilities in the training process. However, the stable embedding layer that they've introduced, they allow for the use of 32-bit optimizer states even when the embeddings are quantized to 8-bit. So this means that the calculations for updating the weights during training can still use high precision even though the embeddings themselves use low precision. So the method they use is the layer is initialized with Javier uniform initialization for consistent variance, and then they apply layer norm before adding the positional embeddings. So this ensures that the variance stays around 1 and it avoids large gradients that could destabilize training. So this offers significant memory savings without altering the original optimizer hyperparameters, and this also facilitates stable training even when more aggressive quantization techniques are used. These are some of the results. Uh, so as we can see, this is the median. This table basically describes the median performance on many NLP and computer vision tasks. We will be focusing on this language model and transformer tasks. So this is for reference. As you can see, this 8-bit Atom and 8-bit optimizers 8-bit Atom reduces the time and mainly the memory saved is huge. So from regular transformers, it's like 8.5 GB saved. So 8-bit is outperforming in terms of memory and speed in all methods. So so this is a pretty good paper, we can say, but let's move on to the next paper, which performs fine tuning. So, most of the times, for most papers, we do not have the time or the resources to perform the complete training. In most industrial use cases, we only need to fine tune existing LLMs. So this paper, Clora, focuses on the efficient fine tuning of those quantized LLMs. This fine-tuning LLMs is a memory-intensive procedure, and models with like 65 billion parameters require over 680 GB of GPU for the 16-bit fine-tuning. So Clora reduces this average memory requirements of fine-tuning a 65 billion parameter from 780 to 48 GB only. So this method also reaches 99% of the performance level of ChatGPT while only require 24 hours of fine tuning on a single GPU. So these are really monumental and these are some amazing results. So let's go into the detail of this architecture. Now, basically, normal fine tuning with is just the base model and the optimizer states, and this parameter updates and the gradient flow Uh, happens normally. LoRa was the quantization of the transformer model, where it's a method that reduces memory requirements by using a small set of trainable parameters. So all of the parameters are not used for fine tuning, only a small set of trainable parameters are used which are often termed as adapters. So the full model remains fixed, and these adapters are only updated during fine tuning. So gradients during SGD are passed through the fixed pre-trained model into the adapter, which is then updated to optimize the loss function. Clora improves this method by quantization the transformer model to 4-bit precision. So instead of a 16-bit transformer, we are using a 4-bit transformer, and we're also using paged optimizers to handle memory spikes. So we will go into the detail of this innovation soon. So the key innovations of this paper are they've introduced a new data type, 4-bit normal float. So that is information theoretically optimal for normally distributed weight. They also utilize double quantization to reduce the average memory footprint. So what they're doing is they are performing quantization and then they are quantizing the quantization constants as well. So this is double quantization and this reduces the memory footprint. And that's also using paged optimizers to manage memory spikes. Now let's discuss the 4-bit normal float. So this quantization approach is different because it balances the data across quantization bins more evenly. Traditional methods may not distribute data as uniformly, especially when there are outliers or a wide range of values. So this method focuses on equalizing the number of values in each bin and optimizing for a normal distribution. So this aims to minimize the information loss during quantization process. So this is particularly suited to a neural network weights that usually follow a normal distribution. So they spread out the outliers more evenly instead of putting them together in a chunk or box and then quantizing them. They spread out the outliers more evenly in the form of a normal distribution, and this way you get a better representation of the whole distribution with smaller number of bits. So this is more efficient than traditional methods. Now, double quantization. So this is a two-step process to compress the quantization constants themselves, which are used in the first quantization steps. So this further compresses the quantization constants to save memory. They implement a secondary quantization process on the constants themselves using 8-bit floats to reduce the memory footprint without memory loss. So this is different from traditional single-step quantization by adding a second layer of quantization for the constants. So this significantly reduces the per parameter memory cost. Paged optimizers are automatic page-to-page transfers between the CPU and GPU. This is more on the computer network side. So for this is for error-free GPU processing. So when the GPU occasionally runs out of memory, they will perform page-to-page transfers from the between the GPU and this CPU. This utilizes the NVIDIA Unified Memory feature. Now, let's compare Clora versus standard fine-tuning. So these are some quantized LLMs, OPT, Bloom, Pythia, and Llama of different sizes from 125 million to 65 billion with different data types. These are evaluated on language modeling and a set of zero-shot tasks. So is the mean zero-shot accuracy using llama models with different 4-bit data types. And as we can see, uh, normal float that they've introduced, normal 4-bit float and dynamic quantization outperforms the other methods in mean zero-shot accuracy. It's even outperforming the normal float data type. Sorry, not normal float data type and the like regular float data type. So, but we can see that double quantization only leads to minor gains, but this allows for a more fine-grained control over the memory footprint to fit models of a certain size. These are also some results on the pile common crawl dataset, and this is the mean perplexity for different data types. And as we can see, normal float plus dynamic quantization is outperforming the other methods. Now, this is a comparison with 16-bit fine-tuning of Roberta and T5 models from 125 million from actually 80 million to 11 billion. Now, they basically they are asking the question, can the lost performance in 4-bit inference be recovered by conducting 4-bit adapter fine tuning? So they have quantized transformers to 4 bits, and they are comparing the inference So in their method, they have conducted 4-bit adapter fine-tuning. With other methods, they have not performed this adapter fine-tuning and only doing 4-bit inference. So uh, as we can see, we observe that for both datasets, we observe that 16-bit, 8-bit, and 4-bit adapter methods replicate the performance of the fully fine-tuned 16-bit base model. Uh, this suggests that the performance loss due to the imprecise quantization can be fully recovered through adapter fine-tuning after quantization. Now discussing Clora with chatbot state of the art. As you can see, Guanaco is the models that they have used with Clora, and as we can see, uh, um, the mean accuracy or zero-shot accuracy, uh, our model, this model is outperforming all the other models. So we can safely say that it is possible to fine tune a quantized 4-bit model without any performance degradation. These are also some results with the different sizes of llama fine-tuned and the corresponding data sets. And as we can see, the all of the results are very comparable to the llama with no fine-tuning results. Now, moving on to our next paper, BitNet scaling 1-bit transformers for large language models. Now, this is pretty like surprising to read at first about having 1-bit transformers. So we will go into the details of this paper and see how they're actually implementing this. This is a very interesting paper. So now, this is a scalable and stable 1-bit transformer architecture. Uh, they introduce bit linear. They basically convert NN dot linear layer, the linear layer of the neural network, into a bit linear layer, and that is created to train 1-bit weights from scratch. So they are performing training from scratch, but they are using 1-bit transformers. So a 1-bit precision for the weights. So they are directly training on the 1-bit precision weights rather than reducing the precision after training. Now, some of the key innovations of this paper are quantization aware training. So this is these models perform well even when their weights are limited to 1-bit representation, and in contrast to other models where they quantize models after training, so they are quantizing during training. So the training happens with those 1-bit representation of the weights during runtime. So they're also deploying different optimization techniques such as model parallelism with high precision for optimizer states and gradients, and employing large learning rates to handle the challenges with training low precision weights. Now this is an architecture diagram. This is the detail of the bit linear layer, and this is the overall architecture. They will basically replace the linear layers with bit linear layers. The input comes in, a layer normalization is performed, and then max quantization is performed to convert the weights into 1 bits, and then that is dequantized and the output is produced. And each of the there's like two blocks of the bit linear layer in every feed forward network, and they're followed by a GALU. And the bit linear, like in the attention projection layers, in the attention layers, in the feed forward layers, bit linear is applied to convert the weights into 1 bit. So the novelty of BitLinear basically lies in its ability to maintain the training stability and model accuracy even with the extreme quantization of weights to 1 bit. So which is obviously not commonly found in other methods. Now, the weights are basically binarized using a sign function, which assigns -1 or 1 based on the weight sign. So if a weight is greater than 0, it's given a value of 1, and if it's less than 0, then it's assigned a value of -1. So, and a scaling factor is computed to minimize the difference between the binarized weights and the original weights. So So the weights during computation, they are -1 and 1, and then a scaling factor is computed for during the dequantization procedure to minimize the difference between the binarized weights and the original weights. The activation functions are quantized to 8-bit precision for the tensor during training and per token during inference for efficiency and stability. So weights are quantized to 1 bit and activation functions are quantized to 8-bit uh, during training, and during inference it's quantized per token. Now these bit linear weights, they're binarized and then they're centralized to have zero mean. So basically, once we get a weight, we first centralize that to have a zero mean, and then we will get its sign +1 or -1, and then a scaling factor is applied post binarization to align with the original weight distribution. The activation functions in bitlinear are quantized to b-bit precision. In these experiments, they have been quantized to 8-bit precision via ABSMAX, while ensuring the output's variance is maintained for stability. This is done by scaling to the range and performing layer norm. And activations before nonlinear functions are scaled into the range 0 and Q8 by subtracting the minimum of the inputs so that all values are non-negative. For the full precision computation, the variance of the output is at the scale of 1 with standard initialization methods, sample timing or Javier initialization, which has a great benefit to the training stability. To preserve the variance after quantization, they introduce a layer norm function before the activation quantization. So in this way, the variance of the output y is estimated as just the expected value of the ln function. Like, yeah, expected value of the ln function, which is equal to 1. So BitLinear uses this variance for its layer norm calculations. They also perform model parallelism using group quantization and normalization. So they partition the matrix multiplication on multiple devices, and that's how they do the model parallelism. But there is a problem with that. All of the parameters which we discussed over here and for our matrix multiplications, alpha, beta, and all, they are calculated from the whole tensors. And so these tensors are not independent along the partition dimension. So what they do is they divide the weights and activations into groups and then independently estimate each group's parameters. So for a weight matrix W, we will divide it into G groups along the partition dimension, and we then estimate the parameters for each group independently. This formula is indicating that for each group G of weights in the matrix W, we calculate this scaling factor and normalization factors based on the values within that specific group. So this allows for localized calculations within each group, facilitating model parallelism without the need for extensive synchronization across different parts of the network. So this reduces network I/O while performing model parallelism. So during training, they use a straight-through estimator, mixed precision training, and a large learning rate. So what a straight-through estimator does is it uses a method that bypasses this non-differentiable functions to approximate the gradients during backpropagation. So basically, since we know that our weights are just 1 bit, if we allow that to pass through our backpropagation, that is going to that is going to really reduce our weights. Uh, re- so that's going to mess up our upgrade basically. So A straight-through estimator, it estimates the gradients of a function. Specifically, it ignores the derivative of the threshold function and passes on the incoming gradient as if the function was an identity function. So basically, when we binarize the weights, their gradient becomes zero. So during propagation, we just bypass the binarization function and directly pass the incoming gradient to the next layer. So one challenge for the optimization is that a small update on the latent weights often makes no difference in the one-bit weights. So this results in a bias gradient in update, which are estimated based on the one-bit weights, especially at the beginning of the training. So straight to estimator ignores those threshold layer and just passes directly on the next layer. They also deploy mixed precision training. So they use both low precision quantization for weights and high precision storage for optimizer states and gradients to maintain training stability and accuracy. They also employ a large learning rate to overcome the insensitivity to one-bit weights to small updates, which helps in achieving faster convergence and compensates for initial training phase challenges. Now, discussing the energy consumption of BitNet, there's a huge bump in the energy consumption. As you can see, matrix multiplication with, let's say, m multiplied by n and n multiplied by b. These are two matrices. Vanilla transformers, the expected energy consumption will be the product of these dimensions, while BitNet uses a sum of these products. So this is like a big bump. So this BitNet trains one-bit transformers from scratch, so it obtains competitive results in an energy-efficient way. So in the next slide, we can see some of these results. So BitNet significantly outperforms state-of-the-art quantization methods. So as the model size scales up, the cost of savings becomes more significant. The difference becomes more significant while achieving competitive performance with the models trained with floating point 16. So as you can see over here, let's compare a 30 billion parameter model, and the energy difference is just huge for between 32-bit and even 16-bit. So BitNet uses only a small fraction of the energy that other quantization methods and regular methods use. Now, these are some zero-shot results. They are comparing the inference energy consumption with the accuracy, and as we can see, BitNet is outperforming the FP16 transformer significantly. The accuracy is comparable or actually even slightly greater, while the energy consumption is much less. Now, this is some comparison with FP16 transformers, and they are comparing the loss this time. So as we can see, BitNet achieves a significantly better loss, and while the inference cost is much smaller to get the same performance as the FP16 transformers. These are also some results. As we can see, if we actually try to perform quantization to just one bit, BitNet it's the only one that's using training bits for the weights, just one bit for training weights, for training as well as inference. And we can see the if we compare the accuracy of, if we like just interpolate one bit weights and we interpolate the accuracy, then BitNet is really, it's actually performing as good as almost as good as 8-bit weights. And as the model size increases, the energy cost reduction ratio increases by 38.8x for 30 billion parameter model. So, and this table I think we've already discussed. Moving on, so with some more downstream tasks, with the BitNet is more stable than FP16 transformer with the same learning rate. We can see we employ a very large learning rate for BitNet to account for the really small weights. So if comparing it to an FP16 transformer, it's like the FP16 transformer can't even perform at all at this learning rate. And these are also some the different learning rates deployed, and the perplexity is compared. So uh, this learning rate actually performs best with the lowest perplexity. So this means that a large learning rate results in better convergence. Now, this is some comparison with post-training quantization, and as we can see, BitNet uh, outperforms all of these post-training quantization methods. While and it's actually the one that's closest to the regular transformer with 16-bit weights and 16-bit activations. So, and as compared to that, BitNet only has 1-bit weights and 8-bit activations. These are some zero shot and few shot results, and as we can see, BitNet performs best among all of these. These are also some more results with different data sets. And as we can see, BitNet performs best in all of these tables. And they also have, yeah, it has the highest or pretty comparable accuracy among all data sets. Now, so the key takeaways from this paper is that BitNet achieves competitive performance and task outcomes while greatly reducing the memory and energy demands compared to traditional models. It follows a similar scaling law as full precision models, so this indicates strong potential for scaling up further in size. So future plans for this paper include increasing the size and training steps of BitNet and exploring its application in other architectures. This is a comparison chart that I've made discussing the four quantization procedures that I have discussed. So as we can see, as far as precision is concerned, LLM is 8-bit quantization, 8-bit optimizers are 8-bit quantization as well. Clora is 4-bit, and then BitNet is 1-bit weights, while we had 8-bit activations. The techniques they use are vector-wise and mixed precision decomposition. 8-bit optimizers use blockwise quantization and dynamic double quantization of a double quantization and also quantization of optimizer states. Clora uses 8-bit optimizers use dynamic quantization of optimizer states, and Clora uses double quantization and paged optimizers as well as the normal float, the new data type. And BitNet uses a bitlinear layer and group quantization. The key innovation for LLM 8 is that it maintains full precision performance with 8-bit weights. 8-bit optimizers preserve optimizer performance. Uh, and Clora enables large model fine-tuning on just standard hardware and GPU. And BitNet scales transformers with just 1-bit precision. LLM-8 experiments were done up to 175 billion parameters. Clora used up to 65 billion parameters, and BitNet just used general large language models, but they've added in their future work to use larger models. LLM-8 has no degradation. 8-bit optimizers are very comparable to 32-bit optimizers, and Clora is also very close to state-of-the-art models, and BitNet is competitive and comparable to full precision transformers. LLM 8 efficiency is that it reduces memory footprint by 50%. 8-bit optimizers also do significant memory savings, and Clora does efficient fine-tuning on limited resources and limited GPUs. And BitNet reduces memory and energy consumption by a big margin. The applications of LLM 8 just include general large-scale LLMs, and 8-bit optimizers are optimizers for various tasks, not just large language models or transformers. And Clora does fine-tuning of large language models, and BitNet is for training large language models with using only a fraction of the memory and energy. So yeah, this is the end of my presentation.